We start with two fundamental classes. A state represents a node in the NFA with a unique ID and a list of outgoing transitions. A transition stores a symbol, an integer, 0 for epsilon, -1 for dot, otherwise a character, and a reference to the next state. These are the atoms of our automaton. An NFA is just a pair of start and accept states. The public matches method takes a regex pattern and a text, compiles the regex into an NFA using compile, and then simulates that NFA on the text. It returns true if the text is fully matched. Compile creates a parser object that holds the regex string and a current position. The parse method kicks off the recursive descent by calling parseExpr. The parser will consume characters and build the corresponding NFA fragment using the construction helpers. ParseExpr handles alternation. It parses a term, then while seeing, it parses the next term and combines them with union. ParseTerm handles concatenation. It starts with an epsilon NFA, then while the next character can start a factor, it parses a factor and concatenates it. This builds the NFA sequentially. ParseFactor first parses an atom, a literal, dot, or parenthesized subexpression. Then it checks for a trailing, or quantifier and applies the corresponding NFA transformation. ParseAtom handles a single character. If it recursively parses the inner expression, otherwise it creates a literal NFA for that character, or dot. Literal builds a simple two-state machine with one transition on the character, or -1 for dot. Factor epsilon creates an NFA that matches the empty string. Concat connects the accept of the first NFA to the start of the second with an epsilon transition. Union creates a new start and accept state, with epsilon transitions from the new start to each of the two NFA starts, and from their accepts to the new accept. Star creates a loop, a new start and accept, epsilon from new start to NFA.start and to new accept, epsilon from NFA.accept back to NFA.start and to new accept. This allows 0 or more repetitions. Plus is implemented as concat, NFA, star, NFA, at least one occurrence. Optional is similar to star but without the loopback from accept to start, so it matches 0 or 1. Simulate NFA tracks the set of all possible NFA states after reading each input character. Starting from the epsilon closure of the start state, for each character it finds all reachable states via matching transitions, literal or dot. Then it computes the epsilon closure of those states. If the set becomes empty, the match fails. After processing all input, if the accept state is in the final set, the regex matched the whole string. Epsilon closure takes a set of states and follows all epsilon transitions, symbol 0, until no new states are found. It uses a stack for depth-first traversal. This is essential to correctly simulate the NFA because epsilon transitions allow the automaton to change state without consuming input. The main method runs a series of test cases covering literals, dot, clean star, plus, optional, alternation, grouping, and edge cases like empty string. Each test prints the regex, text, and the Boolean result. This verifies the engine against expected behavior. You've built a working regex engine from scratch using Thompson's construction. This classic algorithm converts a regex pattern into an NFA and simulates it on text. Understanding this gives you deep insight into how regular expressions actually work and how to implement them efficiently.